there aren't many writing today involved except one part. So I can probably just stay here. But before that, I'm gonna go and discuss the modules until everybody is here. Yes. So if you have checked or haven't, this week's module, week 15, yay. I will publish week 16 sometime this week so I have access to what's going on. I don't think it's, oh, it's published for you. Huh. Yeah, I'm gonna take that out because something needs to be changed, but your final project is there, so that's good. That's the good news. So we are gonna discuss localization, mostly environment decomposition, mapping, then talking about path planning. So we don't have much time. It will be more of theory, but I'll try to make it fun. So you learn a few things going out of this class, and then if you want it, you can continue on your own. At least you know the lingo and some terminologies. But you should have all the information right before there, and you should be able to model a system kinematically, dynamically, develop a control, simple PID controller for it, and then get to this part. Usually, if you do research, you go on your own and learn how the algorithm works because you find the code and then manipulate it. So that's the way it is. So we're gonna actually do the same thing here. For this week, you're gonna have CP24 for today. So it will be due on Wednesday. It's not gonna be due today. And I posted your homework 5. Homework 5 is slightly different from your other homeworks. I'm just gonna go in there. I just added a rubric. So if you see the rubric, you'll see that. So this, we will discuss that Wednesday or Friday, probably Wednesday. I'll try to put it on Wednesday lecture so you have enough time for to work it on the weekend. Question 2, we will talk about it a little bit today, and then you can just go and do it. So this is more exploring someone's code, how the 2 famous algorithms for path planning, they work, and I want you to play around and give me a report. What do you think? So it's kind of more of doing a little bit of research on this one. And for the first one is more problem solving, which we will have an example probably on Wednesday, and then you're able to do that. The 2 questions, like trying to help you to get more points in your homework division, you know, so try to hit all the elements in rubric to get 15 on each one. So you get 30 points here. So overall will help your homework grade. Bless you. Then I also posted the final project. This is due December 12th, but if you submit early, I'll grade it right away. That will help me to grade them sooner because I'm in a tight schedule of grading. A lot of students are graduating. I have to grade theirs first. So I've tried to explain everything here, but generally this is a 2-link robot manipulator. We have seen it before. Here you are going to, you can use your previous codes, even though you work in a team, you can use that because you're part of the development of the code. The goal here is the user will, so there's a two arm manipulator, 2 arm, right? So you can draw the workspace, the donut shape. The user will select a point, okay, in that workspace, and the robot will go to that point. So using PID controller, PD probably is easier to get to that point, and then you plot the responses, like the position, right? And to show that, so that point had X and Y, had to go this, or you can, it's theta, basically your position, theta 1 and theta 2. So the theta 1 chosen was 45. It took you from 0 to 45 the seconds, and then, you know, just the shape of the response. And if you're a graduate student, you have some extra work to do. For undergrads, you only have to pick 1 point. That's done. For graduate student, pick 1 point and then pick another point, go from that. So the first point is your initial condition, right? So your initial condition will change as you go. I have uploaded a code. I don't know if you can see that. So that's my first point. Pick second point, goes there. So if you then plot theta 1 and theta 2, you can see that theta 1 changed it like this, theta 2 like this. The only requirement I have for my controller is the zeta has to be 1. What does that mean? Critically damped, right? We don't want any oscillation because you'll see that in this, like you have that like a jerky movement. You want a smooth motion. It doesn't have to be fast, right? So I leave it to you as engineers to decide. Doesn't have to be too fast, but I don't expect it too slow. I'm giving 10 seconds for every time to reach, but probably somewhere around, I'm not sure if it was shown in, no. I stopped sharing. I don't know if it was shown in Zoom or not, but I will, well, it is part of the assignment. You can click on that and see it. So everyone has to upload an animation, a recording of that motion. So do that. If you're using any help, again, from outside, you have to cite it. The majority has to be your own work. You have most of it already. You really, at this point, don't need to do anything, like to borrow anything from the internet. You should have done so far and learned. I have given you my code for PID controller, for the PD controller, so kind of help you to your approach. You should be able to put these together. It shouldn't take too much time, right? If you have done part of the programming yourself in your team, all right? You won't be able to publish a report using the publish function because you have the user input. You can just create a Word file, put your plots in there, and also write down what was your tuning parameter for your PID, maybe 1 or 2 line of your observation. What do you think happened? What was your approach? If you had a challenge, if you couldn't make it work, write what you have done, where do you think you couldn't finish, right? So at least walk me through. I know how far you've come, so you won't get a 0. So you get partial points for the final project. Make sense? Then convert that to PDF, please. Do not zip anything. Put your M files and this PDF file as part of your submission. So I can grade on Carmen on my iPad quickly. All right. I won't help you much for your final project because it is built on previous assignments. You should already know. I could brainstorm with you your approach, but I would not look at your code. This is your exam. Okay, you should be able to do it. It shouldn't be too hard, hopefully. All right. Now let's go to today's lecture. Any question before I start? I was reviewing this. No? All right. So Brad, you're checking the Discord. If you have questions, you can put in there. If not, raise your hand. It will be a lot of me talking, so try to stay awake, please. I'll try to break in between. So I decided to discuss and talk about localization and navigation, mostly navigation for today's class. So let's say you have a building map like this, could be anywhere, right? You have access to this. Then we have 2 points. Point A is our start point. We want to go to a point B anywhere on this map. Okay. What do you think could be our strategies to get from point A to point B? We have a robot, wheeled robot that has an arm on top of it and is supposed to perform a task in room B or do something, but it starts from point A. What are strategies you think you can use? So can do what? So go right and then go up. Okay, so that's one method. Michael?
Just send out a bunch of rays and whichever one ends up at B, compare them with each other to compare their length.
So when you say rays, do you mean like rangefinder?
Rays as in just like lines that come off of it. And then
So
like
think of it, oh, I have to walk a little bit. So think of it, this is a robot inside the room, has to come out of the door, and there's a corridor, right? And that B could be anywhere. We chose that location. So if you send a signal, a ray, it will hit the wall right away. It can't see through. So this is a 2D map. So it's a section cut of an actual building. This is like a civil engineer asks them to draw a map to design the house, the building. That's what they give you, right? This is the exact map of a building. So if you send the array, it's gonna probably hit the first wall around it. So you are up to something though. You are sending that array. So if you have a sensor on board that is rangefinder, you can see where your obstacles are and where not obstacles. So probably you can move, advance until you hit the obstacle and then you send the range, right? What's the sensor used for that? LiDAR. The 360 could be 360, but has a range of angle, sends the array, and you can, well, you have 3D and 2D, but 2D enough because your robot is not moving up, right? So the height is like you place it somewhere that it will be the maximum height of your robot. And robot sees the obstacle, and where there's no obstacle, it means you can advance forward, right? So that's one way. But okay, how does it know where B is? This is how it would navigate through obstacles. But then how does the robot know where B is? I don't know. You can assume where no B is because there are different methods. So I want us to just explore before I start. I want us to explore to think. This is the thinking part, brainstorming. I have a problem. How can I solve it? So what did you want to say?
Well, I was going to say, you could theoretically just tell the robot to program in where,
That's what my pop said.
distances,
Just go like straight and then go right, right? So that's called programming. You can program hard code what to do because your robot can go straight, your robot can turn right, can turn left, right? So that requires you to know where B exactly is with respect to the map, right? And pre-program, hey, to reach to that point, you have to go 10 meters straight, turn left, 5 meters, then you'll find the door. You have to use your sensor to find the door because you might actually not end up in front of the door because we discussed on Friday, for those of you who are here, there are uncertainties. You might not actually end up where you were supposed to. You might end up in that ellipsoid, right? That might not be the exact where you are. So you have to use the final sensor. Do I find the door or do I have to adjust and find the door and go inside, perform a task?
You could just keep taking right turns until you check everything.
You
And
could do
compare
that.
around
So it's
the
a
different-
rudimentary, like check turns. That requires that there is a pre-installed sensor or a marker on that door. You are exhausting your search. It's a search method. You're searching everything until you find that maybe not the computationally the best way, but sometimes you have to do it when you don't know the map, right? So when John, I think what he meant was, do we know the map of the building or we don't know the map? If we know the map of the building, we can assume pre-program or use your rangefinder, follow this corridor, or like you can have a line follower on the wall, right? If you have a robot in the building is doing things for you, you better have the means for it to be able to work. So follow this line, pretty simple sensor, and then when you finish this corridor, take the left or right, and then follow the line until you again find the door, and then check if you're in the position, then you can enter and perform task B. Okay, whatever happens at point B. So really, if we have the map or not, make a big difference, right? So when we get to navigation, one thing that we need to think of is computational complexity, right? Then there's the structural integrity, which if you have a map, you exactly know where things are, someone has solved it for you, right? In cases, there are cases that we don't have. We have to real time also map the environment, correct? So there are two different problems. Really, the methods that we talk about, you have to see which problem you have and then solve it based on the problem. Now, what you mentioned and what Vaibhav said, when you program is called behavioral navigation, behavior-based navigation. Go straight, turn right, turn left. You still use sensor. The robot still uses sensor, but robot has an understanding, perception, and representation of where it is, right? So Maybe the robot doesn't see everything, but if I tell the robot, go straight 5 yards, turn left, 1 yard, give this flower to 10. Not a flower, but task done, right? The robot doesn't know where it is, but it has the instruction based on the map that is realized, right? So this is called behavioral. Sometimes this actually might be the solution. When you have simple tasks that the robot needs to do, computational complexity comes in play, and this is very simple, right? If you have worked with robots, if you program them, programming hard code is really easy. You have underwater robot, you want to go down, perform a task, go 10 meters down, and then, okay, when you're where you think, check your pressure if you're not going down, right? You just hard code it. Sometimes hard coding is the solution, it gets you, but not when you have complex tasks to do. So this might be the solution to a problem, you know? And it can reach to all the rooms. Maybe it has to go to 5 rooms and inspect if the doors are closed, right? At the end of the shift, that's for this floor. It can be done really quickly by this approach, and it's fast, very cheap, very easy to program. And what learning? Yes, this is just like exactly knows everything. Just turn right. You have it doesn't. So what it does here is you tell the robot go 10 meters. It will check how does it know it went 10 meters forward. Odometry, right? 10 meters forward, and then it looks for something in the environment to check, right? So there's a sensory data to confirm because there's nothing to validate. If we were outside, what would we do? What's the difference? Why we are discussing the inside, the building problem. We usually discuss harder problems, but this is a harder problem. Why is outside an easier problem? There's GPS, right? If you have your ground truth, you know where you started, you have odometry, it's like, I'm going 10 meters, well, maybe more than 10 meters, depending on the GPS signal accuracy. But let's say you're going 20 meters. You're going 20 meters, you think you went 20 meters, odometry, you check, it's like, I'm 10 meters, right? Then you check the GPS, it says you only went 18 and a half if you had that accuracy, right? So you can use that sensor to fix, to adjust, right? And then you go a little bit forward and then you can turn right or left. In the building, we don't have access to GPS signals. When you're testing in the lab, you have the camera system, which is an indoor GPS, but that's for development stage. When you actually use the robot in a work environment, you don't have access to that. The onboard computer has to do all of that. So you will place or you will see features in the building where the robot can verify where it is. You can't just use dead reckoning. Now, as part, what do they do for underwater? Because you don't have access to GPS, you don't have features. So you have to go by dead reckoning. So when you are in a featureless place, environment like underwater in space, the problem becomes even more difficult. So you have to use other methods to be able to collect some data to verify or estimate where I'm actually are, right? So we are thinking about indoor, we have features, there could be a map or we could build a map, right? We don't have access to GPS. We could use sensory data, we can use features to realize where we are, all right? There's always probability. So all of these problems have probabilistic nature in them. The robot can't say 100% on my workplace. Remember in odometry, we had that ellipsoid, right? Because again, always like, I might be 100% here, 90% here, 56% here, but I'm going to be in this area, right? And then when you have that sensor information, I'm 100% here. Make sense? All right. So this is the structure of architecture of behavioral-based navigation. Now, map-based navigation, if you have the map of the area, you already know where things are, right? So you can use perception, your vision sensors, and you can localize. You have a map of building, you know all the features, you know the corners. Then you can plan your motion, move, and you have motion control. So, hey, motors, actuators, move take us 20 meters forward, then you're gonna take a right, and then go to actuator, and you find your way there. As supposed to say by my computer. So the robot attempts to localize using sensor data some information that it had before, which is the map, so exactly knows where things are. Now, the task either could be at a position or at a location. 3 corridors down, you have to do this, or go until you find this marker, then that's your task is, right? This is the information coming with the map. Also has some belief about its position. It knows where it is with respect to the map. So that's the localization part. The robot knows where it is. So there are 2 things. There is the environment, where everything else is. Then there is the position of robot. It's belief that where do I think I am, right? So every time robot updates, where do I think I am? Belief about its own position during the completion of the mission. So let's say the robot started from exact position. It knows exactly where it was at 0 and 0, right? And this is a differential robot. We are using the DDR. It knows that it has to go through that wall. So let's say that's the last part that has to get to point B, right? It has to go through that door. It knows it has to go to the right to start moving. And it might not go on a straight line because remember from if there's this slippage in the wheel, it might not go straight. It always knows though how far it could be from the path. It goes, so uncertainty increases. Why? As it starts moving, it increases. Why is this happening? You see that there, and we have the largest. Well, that is, and then this is part of the largest. I can see the scale here. Why this increase the uncertainty? Someone else? Yes.
First one, they come from a known position. Kind of known.
Right. So the error accumulates, right? So the uncertainty about its own belief is growing. But we know under what function, so we can always compensate. It goes here, and you see that it decreased, and then until here, there is a equal like around where I am. Why did it decrease? What happened here? Andrew. You're not sure.
You have sensors to
So you don't have a sensor to adjust your position, but you're correct. You're using some sensory data because the belief came from, I'm not sure where I am, to, oh, I'm very sure, like 98% where I am. So there must be a tag or something in this frame door. The sensor recognized it. So the uncertainty is lower. So it knows the position, right? So someone put that in there because we have the map, we placed it in the map. So it could be the corner of that. If the distance between these 2 doors is this much, then you are in front of the door. Like, oh, okay, I measured, I'm right there. So I know I'm here. You know, there is a little bit, maybe like you don't know, the robot doesn't exactly how far it's from it, but it recognized it. I'm at the position 98%, I'm right in front of it. All right. So advantage of map-based navigation. The robot knows its position, right? And can tell the human where I am, respect the map. So human also knows where the robot is. And if we plan navigation based on mapping, map-based, we can simply change the map, use the same robot, same algorithm, put it someplace else. So this can repeat itself, right? So you just give the new map to the robot and robot is able to navigate through it. The other advantage is if the robot is making the map as it goes, which is the case of a lot of robots, you're hitting 2 birds with 1 stone. We are mapping and doing the navigation. So the good thing here is that the human can use the map of that environment. So you go in an unknown place, you go to cave or I don't know, exploration underwater, and the robot is able to create the map. So now the human knows the map. So disaster areas, there is a map, but everything changed. There was earthquake, right? Now the robot could have some beliefs, some ideas of representation, but now those create an updated map for the human. That human can perform other tasks. So it's valuable if the robot can map the environment, right? What it has to do, just use sensors. Maybe like using a LiDAR, you can map the area. I can also use rangefinder to like map a 2D slice of the area. So wherever the rangefinder is that high would be the cross section. The disadvantage, there are two main disadvantages. One, you need a lot of upfront development. So computation, it might be expensive because you have to upload the map, put all those features so for the sensor to pick it up. If mapping while moving, then you have all the algorithm to write the coding, having the sensor. So upfront is a lot of work, but because you can then use the robot in multiple different situations with the same algorithm, it should pay off itself, right? So if you use the map, you can use different maps and it will do the navigation on its own. It should be autonomous. If it does mapping, it uses SLAM, for example, then you can just put it in any environment and can map the environment for you. So the goal is not just navigation in that case, it's mapping. So it will pay itself off, the cost of the project. All right. The drawback is, another drawback is that if the robot is mapping itself, it's mapping the environment itself, it doesn't know actually where the robot is in the environment. It creates a belief and trusts its own mapping, right? It thinks that I must be here. So then if the position is not right, the task that is robot doing might not be desirable, right? So there will be a false trust of the position of the belief in the robot. All right. So far we talked about two things, environment and the robot position, right? So these are the two dilemmas when we are using map-based approach. Representation of the environment or the map, representation of the belief itself. So now we're gonna we're going to focus on representation of the environment. We can use a continuous representation or discrete representation. We will also just talk about the belief. I'm not going into that too much because I think the mapping part, if we can solve that, then the belief, the position of robot is related to the environment representation. So the first method is continuous, the exact map of the building, right? With all the lines, all the features, you can use polygons to show there's a bed, there's a door, there's this hallway, you can create everything. This is something that we have to do, an actual map of the building. You can upload this program just to a robot. What's your drawback here? With lots of processing power, right? Depending on the task you're doing, does it worth it? If you want to go from A to B, it could be like turn right, turn left to there. You kind of have to, it's something you have to use exact mapping. So exact mapping, continuous lines is one of the methods. The other method, which you might have seen it more, is line extraction. So now if you have that range sensor, when you're walking through the hallway, you're checking the 2D slice of that building, of that floor, of that map, but you're replacing. You see that if there is like a desk or a closet there, or there is an opening, so there is a closure, I'm going to just show the obstacle part of it. Places that I should not go as a robot, the robot should not go because it will hit. So you're replacing this polygon with lines, right? So this is less features than that. Needs less processing power than this one. Now, if this was the real map, this is the representation with line extraction, and you see that here I said a set of infinite lines. this doesn't mean that these lines are infinite. It means that as many lines you need to extract from feature, you will do it. Just to show the obstacle and the free space. So the robot can be anywhere when it's choosing its location, going from here to that corner, can go anywhere here as long as it avoids the main line. So it needs less power, right? We didn't do anything to the free space. We just identify the obstacle. Don't go toward these. All right. So this is one approach. The other approach is, yes.
Would you program the robot to know its own size?
Yes. So you will have a vicinity circle. So you say that what is the size of the robot? So usually circle or the shape of the robot. So if depending on where your sensor is, this much is like every distance is A plus something. So A is the distance of the robot from that sensor. Because everything you get is that sensor, right? So if you are going to an environment, the robot places itself as a sensor. So that's why you will probably place that sensor on the robot's reference, right? The body reference frame, the sensor would be there if your main navigation was based on that. Good question. Yes.
Would there run into issues where you have let's say, a long hallway with an L, and then the robot's down here looking down the hallway?
Yeah.
It would see the end there, and it would count as just like a dead end, or because you can see the wall going that way, it treats that as closed off. Is that like an issue that they run into, or
No.
is it able to? So
the robot will see this distance, like say 10 meter open, then there's an obstacle, right? It's not going to decide that I'm not going to go there because there's a wall. It's going to go there to vicinity. So you have the vicinity. So check. So if a robot, when you're doing object detection like obstacle avoidance, obstacle avoidance, the robot doesn't really go next to this. So there's a vicinity error. So you will have a sticker bubble, right? If you see obstacle in 0.02 meter, don't go closer. Or you decide how far you can get close. What is it called? Is it vicinity or? It's a term. I think right now I can't remember vicinity. I think it's another word for it. But, you know, there's a word for it. Huh? It's like a buffer zone, but it's like an everyday word. Proximity. Thank you. Because you can have proximity sensor. So there's proximity. Who said that? Next. So proximity sensor or proximity, like don't get closer than this much of the obstacle, right? So you go to that area, if that recognizes there is obstacle, is dead end. So what has to come back? But if it is a corner, so you're going kind of around it with that, right? And then the robot can find its next path. So if you have the map of the environment, you know it's not a dead end. There is going to be like a right turn or left turn at the end of it. If it is mapping, it doesn't know, it has to go. You see that search algorithm? You don't find the first way. You find all the possible ways as you go, and then you map the area. So, this is the obstacle. Let's not go. Or you have to sometimes, depending on the algorithm, like what algorithm, you have to actually go around the obstacle. And then you go back to where you were, and you say, you know what? It would have been easier if I continued. There are some algorithms that would find all the obstacles, you kind of map the obstacles, and then decide, okay, the best way is to go this way through the obstacle. Really depend on what approach you use. Again, calculation complexity, like how much it takes, or what method mathematically is easier to find. Now, the composition is probably something you might have seen or heard. I don't know. This is my favorite because easy to understand, kind of brings you to the digital world. So you will decompose and bring that real math to some abstraction. So when we talk about abstraction, we are kind of losing the reality, right? But in what expense? If we can keep the useful information, then it's good enough, right? So whenever we are doing this, we go from that real continuous map, we are losing some information, right? So it's a trade-off between accuracy and how computationally expensive it is, or structurally true your map is. So do you really need to know how it looks like, or it's just for you the rectangle? That's kind of the composition. So The advantage is that you have less calculation to do, because if you don't have the map of the environment, or if you just have a map but you don't know the pathways, you have to kind of decide, discretize that. So this is, you're going to discretization. So to discretize a path or an environment, what would we do? So let's say, so this is the trapezoidal cell decomposition, which your class participation basically is this a different shape. So let's say you have this classroom. We are gonna say this is a rectangle, square, square, rectangle, square. I'm point initial, and my goal is to get out of here as soon as I can. So how can I go through this obstacle? But there are different ways and how the robot can find this. So we will identify the obstacles. So we kind of know the obstacles. We know the surroundings. So we know the edge of the environment. In this example, this is rectangle, right? So we reduce, let's say this classroom to a rectangle and 3 polygon, right? I can say polygon objects. So we started, so this is the only time that I will actually use my iPad. So this is started as this. So this was your blank slate. You had your obstacles. Obstacles are in the middle. Let's say they're black, or here with hash lines. And this is the environment. So in this method, we are going to identify all the edges. No, sorry, all the vertices. So what does it mean? I'm going to start from, let's say, right left side. And here are the vertices of all of these objects. This is a step 1, right? And then I'm going to number them. Let's say start from 0, 1. How do we number? We start kind of sweeping, and whatever edge comes first, it gets the number. So 0, 1, 2. Oh, sorry, that's not 3. 2, this is 3, 4. And then this becomes 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. So identify all of those, right? So on here would have been this. Now you can have different shapes. If you see your class participation, your environment looks like this. So this is your point, let's say 0. And then you have some object inside. So you have to count your vertices of your environment as well. We're going to use all of that to create this trapezoidal. So let's say we did all of that. Once we are done, we are going to create, we're going to connect these vertices to the edges, a straight line up, a straight line down. So here would be, so these two are already connected, right? So here up, down. This one doesn't have up, just has down. This one has up. This one doesn't have up or down. This one has a down. This one down to here. This down to here, like up to here. Then this one up here. So you end up getting this areas. Now start numbering them. 1, 2, 3, 4, 5, 6, 7. So numbering are how many trapezoidal we have. This number, again, try to follow an order. It just makes it easier for the next round, but it doesn't really, the order doesn't matter. You'll see why. But so this area that's encapsulated in this trapezoid, this whole thing is 1. This is 2, 3, 4, 5. This is 6, 7, 8, and so on. So now that we have this, what we did is we divided, discretized this environment into smaller environments Now, this says that if the robot is here, starts here, doesn't matter where it is, it's in location 1, right? It's in location 2, 3, 4. So now to go from 7 to goal, which is in 15, how would you, what would the robot do? How would it go? There are different ways, right? So when we are doing the navigation, we also are looking at shorter path or optimizing the path waste of time. So shortest path is not the fastest path. So let's go, maybe the robot will go from here in there or goes from here. How do we know which one is the shortest? So one way which A-star algorithm will use, and you will have it in your homework, is that find the midline of all of these lines and then calculate how much it takes you to go. Then you can find your fastest way to get you to your goal. That is the algorithm for A-star. So it comes from decomposition. You decompose your environment. And then, so one way is that, hey, I don't want to pick the middle line. I want to go from the middle of that area to middle of this area. It's fine, but there is a problem that you might actually, you'll see in your homework if you do it, you might actually go over obstacle if you're going from a middle to another middle. So instead of middle of the region or trapezoid, we are gonna shoot for middle of the edge. And that's how we calculate the distances, because when you're in the middle, distance above and below are the same distance far from where you chose, right? And then it will find all the possible ways and calculates how far they are and finds the shortest path. Now, to do that we are going to use adjacency graph. So for the adjacency graph, I'm gonna take this one off. You're going to create this circle, right? This node. So this is graph theory from here. So this is 1, this is 2. I'm probably doing it too large. So you have to do this for your assignment, for your class participation. 2, 3, 4, 5, 7, 8. So identify all of these, 10, 14, 15, 17, 18, there's 16 here. Then what I missed is 11, 12, 13. Now we have to connect these together. This is 5, this is 6. Oh, I had 5. Never mind, this is 6. So how do we connect them? If they share a common edge, they are connected, right? So 1 is connected to what? 7 and 2, right? 1 is not connected to anything else. Then you go to 2, right? If you were writing an algorithm, you wanted your algorithm search based on sequence, right? So you go to now it makes sense what it would have been good to number them kind of in sequence. So you go to 2, 2 is connected to what? Only to 3, right? And to 1, which is connected. Then you move on to 3, 3 connected to 4, 4 connected to 5 and 6, and 11, right? And then you go on and continue and finish this. When this is finished, then you have to find the shortest, all the possible paths, and then you'll find the shortest path. So how do we know what is these values? We'll find it from what these distances are. So we can give a weight to that age, right? The numbers, so then we can use that. Which we'll discuss on Wednesday to find the shortest path. So there is a method to use it. Basically, whatever we discuss here, we're thinking we're writing a code for it, how the algorithm is do. So you should be able to write an algorithm to do this for you, right? Next class, I'll give you an interactive solution to this. But I want you to do the example for class participation yourself. Then you will have that website for you.
When you're labeling the vertices, you didn't label the on page 4 by 5.
I did.
No, sorry, previously when we were like numbering them.
So
would
here,
you leave them out because
so-
there's no line that would go
so
through
I numbered them, but there was no up or down line for it. So I moved to the next one, which was 6. Yes. So you will identify all of them. So if you look at your class participation, the shape is different. Actually, everything I think will have an up and down line. So every one of these is your trapezoid, right? So it means that it doesn't matter where the robot is in this area, it's empty, right? So why we store information about the exact position? The robot is trying to navigate. The goal is navigation. You can go from 1 to 2. If you follow this straight path from middle of this to middle of this, you're good to go, right? That's how A star, for example, works. You can actually start question 2 of your homework, and it will give you a better idea. And the other method is just different approaches, kind of the same approach, but more, I won't tell what, because that's part of your problem for your homework. But you will see that they kind of have the same approach, but slightly different, yes.
So does this only work when you have the map already?
You didn't have, well, you had yes, you know the edges of your environment, you know where the obstacles are, right? That's it.
Okay.
So kind of you have the map, yes, you're decomposing the map that you currently have. So you know the position of the obstacles.
So would this be done prior to the robot for being involved?
Yes,
or
you
would the robot
upload
be
this.
placed in that environment, map out the room, and then do these calculations, and then navigate?
So you upload the map to the robot, right? Now, the robot should do the composition because you can start from any point in this map to go to any point in this map, right? So the composition should be done by robot, and you'll see there are different methods. So this is your homework, your class participation you should be able to do. You'll see that there are different ways. We have fixed the composition. So we are saying that, okay, now let's decompose our obstacles as well, right? So here, this is inexact, and the problem with this inexact decomposition is that you're kind of losing these points that the robot could go. So whenever it's black, it says that proximity, don't go there. It might have, you might be able to find a way going through those, but you're saying that don't go, that's going to be an obstacle. There is another way, adaptive. The adaptive says that, hey, divide them in boxes, let's say 5 by 5 meter or 5 by 5 unit. If you don't reach any obstacle, move on, don't decompose more. Decompose another 5 by 5 until you reach an obstacle, then decompose that one is smaller. If there's no obstacle, move on. If there's obstacle, is smaller. So in adaptive method, you are saving a lot of processing power, right? Because you're not dividing, decomposing the whole environment. You're trying to, okay, this is an available free environment. Why do I have to decompose it more? But this is for the run from me to go to you. But if you're in another case, I have to go from here to Megan. I have to do this again, right? So this is online mapping. So you're doing, you know the environment, but you don't know all the paths going through. I only know from this place to this place goes through this rack. So the robot should be able to do that online. So this adaptive is very useful because it saves you a lot of calculation, but maybe it's not able to map the whole thing that you use it. You have to do it every single time, or it's faster, so it makes sense. Other method, you can create occupancy grid, which if you have a rangefinder, you kind of are saying that, hey, I'm going to use my rangefinder, extract all the lines. These are all the areas that are occupied. They're all the areas that are free. And navigate through, right? So you see that the environment can be decomposed, let's say your map, in different ways. To be useful for navigation, depend on really your problem, your robot processing power. It's not cheap to buy a computer to put on a robot. Projects have limitation for the budget. You choose the best way, the fastest way, right? For that application. So this is basically the end of this lecture. The belief is, let's say that that's robot position in real life. Now, if I have line-based mapping, The robot maybe knows its position X, Y, and theta with respect to that. If I have decomposition, so it knows what grid it is. If I have a topological map, it has the node. So the robot belief is based on the map, right? So in one of them is what grid I am, in one of them is what is my X, Y, and theta. So really, but this is called single belief because there's one idea about where it is. We might not be accurate, but that's what it thinks. Multiple belief is that I might be in this area 90%, 80%, so there's more probability involved. You'll see use of Kalman filtering here. It's using different sensors. As you get closer to where you want to be, you have more data. So you see that in number 4 here, there are more obstacles exactly those, like, or has a higher probability of the belief than where it is. So kind of comes from the accuracy of the sensor and the data it gets. There's multiple belief, it helps. We're using different sensors, using them to realize where the position of the robot is. Right? They always is probability. Trump's a single representation, single belief, but needs more processing power again. All right. Do CP24 by Wednesday and remind me to give you that website that has interactive